Hello students, welcome to the lecture on knowledge management and systems, and after this lecture we will be able to learn the following objectives. Describe knowledge support system, explain the artificial intelligence, discuss neural network and explain virtual reality. Let's discuss about knowledge management and system. The issue of knowledge management system has probably always been the most discussed and debated topic within knowledge management KM. Even though knowledge management systems are not the most important part of KM, this is still the subject that generates most interest. We have considered the impact of IT in all the knowledge management strategy subsections, with particular emphasis on its role in knowledge sharing. The problem is that rarely are both these sets of knowledge known by a single person. Moreover, technology is rarely designed by the people who use it. Therefore, firms are faced with the issue of fit between IT systems and organizational practices, as well as with acceptance within organizational culture. Bota et al. Stress the importance of understanding what knowledge management system cannot do. They point to the fact that introducing knowledge sharing technologies does not mean that experts will share knowledge. Other initiatives have to be in place. Identify several additional failure factors, including lack of top management support, organizational culture, lack of a separate budget, and resistance to change. Building upon all this and incorporating previously discussed elements, failure factors of knowledge management systems are as follows: inadequate support, managerial and technical during both implementation and use, accepting that the technology is a KM solution in itself, failure to understand exactly what the firm needs, whether technologically or otherwise, not understanding the specific function and limitation of each individual system, lack of organizational acceptance and assuming that if we build it, they will come, lack of appropriate organizational culture, lack of organizational or department, etc. fit. Does it make working in the organization easier? Is the system appropriate in one area of the firm but not another? Does it actually disrupt existing processes? Lack of understanding of knowledge dynamics and the inherent difficulty in transferring tacit knowledge with IT-based system. See segment on tacit knowledge under knowledge sharing. Lack of a separate budget. According to the process of successful implementation have three stages: adoption, acceptance, and assimilation. Based on recognized models and theories, the authors identify three comprehensive sets of factors affecting these three elements. The resulting models organize the KMS implementation factors into the following categories: influence by design, innovation characteristic, fit acceptance results, communication characteristic. Not influenced by design, environment, technological infrastructure, resources, and organizational characteristic. Influenced by design, effort expectancy, performance expectancy. Not influenced by design, social influences, attitude towards technology use. Influenced by design, social system characteristic, process characteristic. Not influenced by design, management characteristic, institutional characteristic. Knowledge support system. Now we are moving on to our next topic, that is knowledge support system. Knowledge management support system require new design principles because knowledge fundamentally differs from information and data in organization. Knowledge in an organizational members' experience and values combined with and shaped by the information contained in various systems and data provided to the person. It is intrinsic to organizational members and focuses on the information recipient. In contrast, data refers to a set of discrete objective facts about events recorded in an organization, and information provides organizational members with contextual meaning to data. Knowledge can be tacit or explicit. Tacit knowledge is the beliefs and values that are hard to express but inferred from the behaviors of organizational members. Transaction processing is a computer-based group of logical operation. In order for transaction processing to work, all the operation must succeed or fail as a group. A simple example of transaction processing is paying a utility bill from our bank account. The process of paying a bill from our account consists of debiting our account by, say, INR 100 and crediting our utility provider's account. This may seem like a simple transaction, but it may actually consist of several sub-operations. If the debit of INR 100 was successful, but the credit did not go through the utilities provider account, then the transaction would fail. Our INR 100 would be lost somewhere in the transaction. The transaction processing system allows all the operations to be grouped into a single transaction in order to prevent problems in consistency. System capable of transaction processing must pass tests for atomicity, consistency, isolation and durability, otherwise known as the acid test. Transactions are known as atomic, meaning that the transaction will either happen or not. If one account is debited, then another account has to be credited. The transaction processing system must always be consistent with its own rules. If errors occur in the transaction on either side, then the transaction will fail. Isolating transaction means that other processes never see information during the transaction. They may see information before or after the transaction, but not during the transaction. For example, if two people are booking the last theatre seat at the same time, they can both see the seat before the booking, but only one person will succeed in booking that seat. Transaction must be durable. This means that when that final seat in the theatre has been booked and we have received notification that the seat is ours, it is permanently recorded. No matter what problems occur to the system, there are backups in place in the transaction processing system to ensure that the record stays permanent. The advent of the internet has seen a booming transaction processing system and software. Over the years, the cost of buying and implementing the necessary software has dropped so much that most businesses can apply it profitably. Banking from home, booking a holiday on the net, shopping and working from home are all now readily available and less time consuming thanks to transaction processing. Transaction processing (TP) has been successfully used in database applications from decades. The basic principle of TP is to provide application with concurrent, reliable and efficient access to shared data sources. Classical transaction processing has been well understood and highly researched through the design and development of numerous models, protocols, frameworks, prototype tools and commercial systems. The current widespread technological advancement in computer system, software application, communication networks and mobile devices provide new platforms such as Web X.0, cloud services, Internet of Things, or mobile and pervasive computing. These new platforms create new challenges for transaction processing. These challenges are to deal with environments wherein computing devices and services are context-aware, adaptive and responsive to the user's needs and the execution environment. The aim of this symposium is to provide a forum for researchers and practitioners in order to present the current research work on the advances in transaction processing. The main topics to be addressed include, not limited to, advanced transaction models and protocols, failure and recovery of transaction, testing of transaction, performance and efficiency of transaction, new correctness criteria and properties of transaction, transactional web services and SOA, cloud service provisioning using transactional application, context-aware transaction processing in the web, Internet of Things, mobile and pervasive transaction, transactional memory. Artificial intelligence. One thing it could be is making computational models of human behavior. Since we believe that humans are intelligent, therefore models of intelligent behavior must be AI. One way, which would be a kind of cognitive science, is to do experiments on humans, see how they behave in certain situations and see if we could make computers behave in that same way. Imagine that we wanted to make a program that played poker. Instead of making the best possible poker playing program, we would make a one that played poker like people do. Another way is to make computational models of human thought processes. This is a stronger and more constrained view of what the enterprise is. It is not enough to make a program that seems to behave the way humans do. We want to make a program that does it the way humans do it. A lot of people have worked on this in cognitive science and in an area called cognitive neuroscience. The research strategy is to affiliate with someone who does experiments that reveal something about what goes on inside people's head and then build computational models that mirror those kind of processes. A crucial question is to decide at what level to mirror what goes on inside people's head. Someone might try to model it at a very high level, for example, dividing processing into high-level vision, memory, and cognition models. They try to get the modularity to be accurate, but they do not worry too much about the details of how the models are implemented. Other people might pick the neuron as a kind of computational unit that feels like it is justified in terms of neurophysiology and then take that abstract neuron and make computational mechanism out of it. It seems justified because we know that brains are made out of neurons. But then, if we talk to people that study neurons, we find that they argue a lot about what neurons can and can't do computationally and whether they are a good abstraction. So maybe we might want to make our models at a lower level. So it is hard to know how to match up what we know about brains with computational models. Another thing that we could do is build computational systems that behave intelligently. What do we mean here? When we talk about human behavior, we said that it was intelligent because humans are intelligent. So what humans do has to be intelligent. In this view, we say that there might be other ways of being intelligent beside the way humans do it. And so what we might want to do is make computational system drawn from this larger glass. But then we get into terrible trouble because we have to say what it means to behave intelligently. We might feel that although we cannot define what it is to be intelligent, we can recognize it when we see it. We will give up on trying deciding what intelligent is and spend our time thinking about rationality. We will get into that in more detail later. So, the perspective of this course is that we are going to build systems that behave rationally, that do a good job of doing what they are supposed to do in the world. But we are not going to feel particularly bound to respect what is known about how humans behave or function.
Artificial intelligence. The phrase may send a shiver down your spine, suggesting images of Terminator robots bent on world domination.
Listen to me very carefully.
But today's intelligent robots, advanced as they might be, are more like toddlers than Terminators, trying to grasp the world around them.
That wasn't great. So it turns out that getting robots to recognize things from a picture is one of the most difficult things for robots to do. So we often end up writing fairly large amounts of software to, say, recognize what a computer mouse is or what some other object is.
To cope with complex tasks like object recognition, top AI researchers like Stanford University's Andrew Ng wrestle with problems in computer science, cognitive psychology, math, and even philosophy when trying to demonstrate intelligence in a robot.
When you think about human intelligence, I think people can do a lot of things, and when robots start doing some of the same things that we think of as requiring cognition or reasoning or thought, that's when we think of our robots as starting to be intelligent as well. For example, if you have a robot recognize a new object it's never seen before, or if you have a robot able to navigate a building that it wasn't explicitly programmed to navigate, these are examples of what we think of as artificial intelligence.
Have it your mind.
building a robot that can recognize new objects and size up new environments. It's all in a day's work for STARE, the Stanford Artificial Intelligence robot.
On the STARE project, our goal is within a decade to develop the technology to make it useful to put a robot in every home. Many of us spend lots of time today on household chores like tidying up and cleaning and cooking. And on the STARE project, I'd like to build a robot that can do many of these things for you.
Before STARE, there was Shaky, the first artificial intelligence robot, created in 1966 at the Stanford Research Institute in Menlo Park. Since Shaky, computers have gotten far more nimble. Why hasn't AI made similar gains? Well, with AI, the intelligence lies less in the hardware and more in the software. And writing the code, or algorithms, to make machines smarter has been tricky.
The computer algorithms really lie at the heart of making the robot smart enough to carry out all the tasks we want it to do. To implement these algorithms often requires that the programmers have a deep understanding both of computer science principles as well as of robotics principles, how to move things around and what different sensor readings are telling you about what's out there in the world.
And looking at the world through STARE's eyes offers a new perspective, or more accurately, a whole new dimension.
When you're building a robot, you can often endow it with extra sensors that we as people don't have. One of the extra sensors we have on a robot is a laser scanner. And what it does is when it's trying to figure out the three-dimensional shape of something in front of it, it plays a laser over what's in front of it. And by seeing where the laser beam falls and doing some math, it can actually compute the 3D position of a lot of points in front of the robot.
But seeing the objects around it is only part of the challenge. STARE then has to be able to recognize them if it's going to interact with them.
So the way the robot learns to recognize objects is we actually show it lots of examples of, say, bicycles or coffee mugs or slippers or whatever. What a computer actually sees is a lot of numbers like these, and it tells you for every pixel in that picture exactly how dark or gray it is. And so a small number is a light pixel and a big number is a dark pixel. And the job of a robot is to look at a lot of numbers like these and figure out if there is a sleeper in those numbers.
And when it comes to learning, it turns out that even machines can respond to a little positive reinforcement. Here, numbers function as rewards.
So one way of thinking about this is that it distills down the notion of rewards down to a mathematical formula in which we use a number to tell the robot how well it's doing. And so every time your robot does something good, the reward function outputs a large number, and that tells it has done well.
AI is about more than making robots smarter. It's also about getting computing applications, like those used on the internet, to think, even reason, more like humans. Daphne Kohler of Stanford University is using AI to make image searches more accurate by teaching the computer to understand context.
A computer system by itself is pretty dumb. It doesn't know things that are obvious to you and me. And so everything that a computer system knows is going to be something that you have to either tell it or better, and this is the revolution that we're undergoing, have it learn by itself by seeing enough examples of real images. So here is an example that we are using for outlining giraffes. Initially, what the system is given is a bunch of examples of a giraffe that are outlined for it. For each of these dots, there's actually a machine learning algorithm that learns to rank different pixels, different regions in the image and say, this is a plausible place for this purple dot as opposed to this, which is not so plausible. And the algorithm figures out that this dot on this giraffe corresponds to, is the same kind of position as this dot on this giraffe. It learns how to make these distinctions, just like a human child, once it understands what giraffes look like, can understand the difference between standing up and leaning down with 2 or 3 examples. The computer system can do the same thing.
Working with AI is like teaching a child. It requires a lot of patience and flexibility.
So obviously here the algorithm made a mistake. It's a pretty bad mistake. If you actually look closely, you can try and understand why it made the mistake. There's actually sort of contour lines here where the zebra is confusing it and it's looking like it's seeing a leg. And so there's actually two types of learning that one can do using an example like this. One is training the algorithm and one is training us, the person designing the algorithm.
But even if a machine can learn from mistakes, is that really intelligence? Will there ever be a truly intelligent machine, one that rivals us in its ability to reason?
The human brain is maybe the most amazing computer that we know of in the entire universe. The brain has 10 to 11 neurons. That's a 1 followed by 11 zeros. That's a huge number. And today, we barely understand how the brain works.
But how the brain works and its structure may hold the key to a new kind of thinking machine. Just ask Dharmendra Moda, an IBM engineer at the Almaden Research Center in San Jose.
If you could map out the blueprint of the wiring diagram of the brain, we could then use the wiring diagram of the brain as a starting point to create a new generation of computers.
Dharmendra's road to reverse engineering the human brain has begun on a slightly smaller scale.
One of the achievements of my group was that we were able to map a rat's brain onto a modern-day existing supercomputer. What we are looking at here is a simulation of the rat's brain. The top two panels represent the right hemisphere, the bottom two panels represent the left hemisphere.
This model of rat brain activity is an important step in their quest to build an artificial brain, where processors may function like neurons and synapses.
Imagine taking this visualization and underlying computational engine becoming the new paradigm in computer science.
What kind of world does this herald? Will thinking machines soon exert significant control over our day-to-day existence? Probably not. While the hardware exists to carry out such brain simulations, the software to make the cognitive computer reason and multitask like a human brain remains elusive. For now, that is. But in the field of AI, it pays to think big and be patient.
I think that of all the things we could be spending our time doing, what could be more exciting than trying to build systems that are as intelligent as you and I are? And whether it'll take us 10 years or 50 years or 100 years to figure out, I don't really know.
Now it's your stapler. Use it wisely.
But I'm an optimist. I do believe that someday computers will be as intelligent as you and I are.
Goodbye.
Let us discuss about neural network. A neural network can be defined as a model of reasoning based on the human brain. The brain consists of a densely interconnected set of nerve cells or basic information processing units called neurons. The human brain incorporates nearly 10 billion neurons and 60 trillion connection synapses between them. By using multiple neurons simultaneously, the brain can perform its function much faster than the fastest computers in existence today. Although each neuron has a very simple structure, an army of such elements constitute a tremendous processing power. A neuron consists of a cell body, soma, a number of branches called dendrites, and a single long branch called the axon. While dendrites branch into a network around the soma, the axon stretches out to the dendrites and somas of other neurons. It is the schematic drawing of a neural network.
We all use computers every day. But sometimes, computers fail us. And this upsets a lot of people. What we'd like is for our computers to be smarter and more user-friendly. So some people think we should try to make them more human. This would involve making computers think more like people. But to do this, we first need to understand how humans think and how our brains work. First though, let's look at computers as they are today. Despite everything they can do, they're pretty simple. They take some inputs, perform some calculations, and produce some outputs. The human brain, however, is extremely complicated and a lot of very smart scientists are still struggling to understand how the whole thing works. One thing we have known for a while, though, is that the tiniest components of your brain that makes it think and do smart things are special cells called neurons. Your brain has billions of these neurons, and they talk to each other using electrical impulses to create what are called synapses. This mass of synapses is what is responsible for making your brain think and have a consciousness. Some computer scientists had the idea that we can make a computer that is modeled after this system of neuron connections. They called their idea neural networks. The idea behind neural networks, or neural nets for short, is that we have nodes that have some connections between them. This is similar to the neurons in your brain and the synapses they form. To get a neural net to do something, we trigger a node with some input, and that node in turn triggers the nodes it is connected to. But this alone is not very useful, so we usually organize the neural nets in a way that makes it easy to produce good results. Since we're used to the computer model of computation, we like to have well-defined input and output nodes. We also like to have directed connections, so that we know which way information is going. Not only that, but we want our connections to have different values. That is, some connections should be more important than others. Here the connection values, called weights, are represented by the thickness of their arrows. The purpose of having different connection weights is that it allows our nodes to behave more like real neurons. When a node is stimulated by two different nodes, it can decide which of the two is more important to it by their connection weights. Here, nodes A and B have been given the values green and orange, and they try to pass on these values to node C since they are connected to it. Since the connection weights between B and C is much larger than the connection weight between A and C, node C decides B is more important to it and takes its value. More often though, we design nodes to take a sum or an average of the nodes triggering it. Here, node C takes a sort of yellow color, but notice the shade is much closer to orange than it is to green, since node B's connection weight is large compared to node A's. In some cases, we'd like for our nodes to be able to decide whether they want to accept our triggers at all. So each node gets to think about what it will do. To decide, each node is given what is called a transfer function to judge its inputs. Since in the real world computers treat all data as numbers, the transfer function is a math equation. It's usually not that complicated. After the node makes a decision, it sets its value, and then it can trigger the next set of nodes with that value. Choosing whether or not to accept the triggered value is most useful for the output nodes, since these are the nodes that produce the results that we actually want. Usually though, the transfer function will return a value that is a combination of the node's current value and the trigger value. So using the connection weights and transfer functions, the neural network takes its inputs and produces outputs. This is the same task that a computer would do, but it's done in a way that is similar to the way neurons work. Since the input and output nodes are the ones that matter to us, we consider the nodes in the middle hidden nodes. They do most of the work, but get the least credit. Now that we know the basics, we need to ask some questions. One of the most important questions is, how are the connection weights determined? Well, it turns out the neural networks can learn them. Does this make neural networks smart? Sort of. But it also turns out that the neural networks are very slow learners. Very slow learners, as we'll soon see. But the question is, how do they learn? It's done through a process called backpropagation. We start with random connection weights. Then, for a given set of inputs, we decide on a set of desired outputs. Using the random weights, we first let the network calculate some outputs. Then, we compare the outputs that the neural net calculated to the desired outputs that we defined. Since we gave the network random weights, we obviously cannot expect the two outputs to be equal. So we find their difference. We call this difference the error in the network. This is difficult to illustrate with colors, but you'll have to trust me that I did it correctly. For an easier to follow example, I've given each node a numerical value. You can see that we find the error by simply subtracting, and then we can have negative errors as well. Now that we have the errors, we need to adjust the connection weights to try to produce smaller errors. This is where the backpropagation comes in. The output nodes tell the hidden nodes they are connected to about their error, and together they decide on how to adjust the connection weights between them. The new weights are calculated using an equation based on the old weight, the node's input value, the error, and something called the learning rate. We'll get back to the learning rate later. With the weights adjusted, the hidden nodes calculate their own error using a similar formula to before. Then, these nodes with their newly calculated errors push the errors back through the hidden nodes and adjust the weights behind them. This goes on until all the weights have been adjusted and all the nodes have been assigned an error. The idea is to determine which nodes are most to blame for the error in the output and try to adjust their weights the most. Now that all the weights have been updated, the network tries out the original inputs again and tries to calculate some outputs. The calculated outputs should be closer to the desired outputs than before, but there will still be some error. So the whole process is repeated again, and again, and again. Remember how I said the neural nets are slow learners? Well, the neural network has to do all that for each different input set, and there's usually a lot of those. But the idea works, and eventually the network will produce the desired outputs. To try to produce the desired outputs more quickly, we can try adjusting the learning rate. And we can change the number of nodes as well. But it will still take millions of attempts for the neural network to get the desired output for even a simple problem. So, can neural networks make computers think more like humans? Probably not, but it's a good baby step.
An artificial neuron network consists of a number of very simple and highly interconnected processors, also called neurons, which are analogous to the biological neurons in the brain. The neurons are connected by weighted links passing signals from one neuron to another. Each neuron receives a number of input signals to its connection. However, it never produces more than a single output signal. The output signal is transmitted through the neuron's outgoing connection, corresponding to the biological axon. The outgoing connection in turn splits into a number of branches that transmit the same signal. The signal is not divided among these branches in any way. The outgoing branches terminate at the incoming connection of other neurons in the network. Represent connection of a typical ANN and shows the analogy between biological and artificial neural networks. The neurons are connected by links and each link has a numeral weight associated with it. Weights are the basic means of long-term memory in ANNs. They express the strength or in other words importance of each neuron input. A neural network learns through repeated adjustment of these weights. Let's discuss about virtual reality. Virtual reality VR refers to a technology which is capable of shifting a subject into a different environment without physical moving him or her. To this end, the inputs into the subject's sensory organs are manipulated in such a way that the perceived environment is associated with the desired virtual environment VE and not with the physical one. The manipulation process is controlled by a computer model that is based on the physical description of the VE. Consequently, the technology is able to create almost arbitrary perceived environments. Immersion is a key issue in VR system as it is central to the paradigm where the user becomes part of the stimulated world rather than the stimulated world being a feature of the user's own world. The first immersive VR system have been the flight simulators where the immersion is achieved by a subtle mixture of real hardware and virtual imagery. The term immersion is a description of a technology which can be achieved to varying degrees. A necessary condition is Ellie's notion of a VE maintained in at least one sensory modality, typically the visual. For example, a head-mounted display with wide field of view and at least head tracking would be essential. The degree of immersion is increased by adding additional and consistent modalities, greater degree of body tracking, richer body representation, decreased lag between body movements, and resulting changes in sensory data, and so on. As the timer defines immersion as a feeling of a VR user that his VE is real, analogously to Turing's definition of artificial intelligence, if the user cannot tell which reality is real and which one is virtual, then the computer-generated one is immersive, a high degree of immersionism equivalent to a realistic VE. Several conditions must be met to achieve this. The most important seems to be small feedback lag. Second is a wide field of view. Displays should also be stereoscopic, which is usually the case with head-mounted displays. A low display resolution seems to be less significant. According to Slanter, an immersive VE, IVE, may lead to a sense of presence for a participant taking part in such an experience. Presence is the psychological sense of being there in the environment based on the technological founded immersive base. However, any given immersive system does not necessarily always lead presence for all people. Presence is so fundamental to our everyday existence that it is difficult to define. It does make sense to consider the negation of a sense of presence as a loss of locality, such that no presence is equated with no locality, the sense of where self is as being always in flux. Summary. Now in the end, let us summarize what we have learned in this lecture. Even though knowledge management systems are not the most important part of, this is still the subject that generates most interest. The problem is that rarely are both these sets of knowledge known by a single person. Moreover, technology is rarely designed by the people who used it. Knowledge management support systems require new design principle because knowledge fundamentally differs from information and data in organization. This requires organization to provide a working infrastructure composed of a set of knowledge management support system KMSS and meaningful policies for knowledge sharing. The information shared among members should reflect their values and beliefs about the information stored and exchanged to support KM. As KMSS are embedded within an organizational system, they must also be designed to fit within the cultural values, authority structures, and other design features of the organization.